Okay, part two. Let's talk about why this is happening. So, why when we take a non-zero number and raise it to mod six, or raise it to six in our mod seven system, that do we get one? There's various proofs for this. I'm going to kind of emulate the one in the book. It's not going to be a full proof. It's more of a convincing argument. At least I hope you'll find it so. And we're going to use the fact that exponentiation. Is directly related to multiplication. And in simple systems, particularly when you're dealing only with integers, we can really think about exponentiation as repeated multiplication. I'm going to emphasize that that is not necessarily the way we like to think about it when we start to allow for exponents and bases that are particularly exponents that are non-integer, but since we're only looking at integer values here in our mod system, that's a fine generality that we can take a look at. Okay, so we're going to start by looking at the row 5 in the multiplication table. So if we come over here to the top table and we look at row 5, the thing that we notice here is the fact that every single non-zero number, again, we're only dealing with non-zero numbers, but every single non-zero number in mod 7 is accounted for. We have 5 times 1 is 5, 5 times 2 is 3, 5 times 3 is 1, and so on and so forth. So we get all the non-zero numbers 1 through 6 in this row. Okay, so that's really important. Okay, this is based on kind of an important fact from chapter 8 that may have been, off the radar then, but it is really important now, and that's the fact that every non-zero element of mod 7 of Z mod 7 appears exactly once in each row. Okay, this is relying on the fact that we're dealing with a prime modular number. We'll take a look at some stuff later when we're not dealing with prime numbers, but right now this is really based on dealing with a prime base. Okay, so we're looking at mod 7, and just for our purposes, the theorem I'm referring to is theorem 8.3.4, I think, 6, yes. Okay, so that's what we're looking at. So what this is really saying, when we think about the equation 5 bar x equals 3 bar. What this is really saying, at least based on what we did in chapter 8, is that I can solve this equation. Okay, because we're dealing with the fact that 7 is a prime modulus, so 5 is relatively prime to it. In fact, all the numbers except for 0 are relatively prime to it. So we can solve this equation, and more importantly, we can solve it uniquely. Okay. In other words, when I go to solve this, I can find something. I can find a multiplicative inverse of 5 that I multiply by 5, and I do the same thing to the 3 bar, and I'll get one value of x. And in fact, what do we get? We notice that happens up here when we're looking at 5 times 2 in the table. So that's the unique answer. Okay, notice there's no other point in that row where we see a 3. So I'm not going to be multiplying by anything else. There's only the one value. So this is really important in establishing the fact that we're talking about the existence of a solution and the uniqueness of the solution. We're going to rely on that. We're going to rely on that to go ahead and make our argument for why this works. Okay, so it's important to think about that way. So we have 5 bar times x equals 3 bar. It doesn't matter what we choose for the 3 bar. I could do 2, I could do 6, I could do 5. There's a unique solution out there. Okay, and that's the important part, and we can see that in our chart. Okay, so that is kind of our key. So I'm going to slide things up a little bit. So what we're going to do next is going to require a little bit of clever manipulation. To be honest, it may not be something that someone would automatically kind of come up with without kind of spending a lot of time at it, which is why I'm not going to ask you to prove. I didn't ask you to prove something like this. but we'll take a look at an interesting piece of it. So I'm going to just rewrite the relevant portions of the multiplication table for us. So for instance, we know that 5 bar times 1 bar equals 5 bar. We know that 5 bar times 2 bar equals 3 bar. 5 bar times 3 bar equals 1 bar. We know that 5 bar, can't write today. 5 bar times 4 bar equals 6 bar. 5 bar times 5 bar equals 4 bar, and 5 bar times 6 bar equals 2 bar. Okay. So again, unique values for all of those. But here's where it's going to get a little interesting, because what I'm going to do is I'm going to multiply. So basic rules of multiplication and addition still apply to our modular system. So just like back in Algebra 1, you wanted to multiply both sides of an equation together, or both sides of one equation into both sides of another equation, you could do that. And so what I'm going to do is I'm going to multiply the left-hand sides of all of these equations together. So I get 5 bar times 1 bar times 5 bar times 2 bar, 5 bar times 3 bar, and 5 bar times 4 bar, 5 bar times 5 bar, and 5 bar times 6 bar. Okay? No problem. Of course, if we're going to do that to the left-hand side, we should do that to the right as well. So we get 5 bar times 3 bar times 1 bar times 6 bar times 4 bar times 2 bar. Okay? Looking good so far. Well, here's the fact that we're working with a field. So it has all of those properties that we're used to working with: associativity, commutativity. We don't actually need the multiplicative inverse at the moment. We will in a minute, but we don't need it at the moment. So we can rearrange all of this. So I'm going to rearrange the left-hand side like this. I'm going to pull all the 5s. I'm basically going to regroup and change the order. So I get 5 bar times 5 bar times 5 bar times 5 bar, 5 bar, and then times 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. Oops. A little premature with the equals. 6 bar. Okay? And then just for the sake of argument, I'm going to just rearrange the right-hand side as well, because again, commutative property. 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar. You might see where I'm going here. Okay? So you'll notice that these two things are the same. Okay? I didn't really have to rearrange the right-hand side. Commutativity is still in there, so we can establish that. But what the nice part is, and again, this has to do with the fact that we're dealing with a prime modulus here. And the theorem number I'm going to invoke on this one is 8.3.2. Here's the best part. We can cancel out the things that are the same on both sides. Just like we're working with normal integers. I can divide them out. I'm not technically dividing, but all these multiplicative inverses exist because we're in our prime mod. And so essentially the 1 bar through 6 bar gets canceled out, and we're left with 5 bar times 5 bar times 5 bar times 5 bar times 5 bar, which I can rewrite that as 5 bar to the 6th. But if I cancel out the rest of it from both sides, what am I left with on the right-hand side? 1 bar. And was there anything special about 5? Not really, except for the fact that it's non-zero, but we established that. But it was really crucial that we were in a prime modulus in order to do it. That was important. So nothing special about the 5. I could have done this with any one of the other values in mod 7. Nothing, again, particularly special about mod 7, except at the moment we're dealing with a prime modulus. We'll talk about some stuff that comes up when we're dealing with non-prime moduluses later in another video, but it works for prime mods here. Again, what I said at the beginning, not a proof. This is kind of by example. It gives us some stuff to look at. You'd have to flesh it out in more general terms, but hopefully it's a convincing argument. Okay? We will take a look at some other stuff in a bit.